This is my first time speaking in a situation where there's no speakers, right? So I can't really hear how I sound to you. So this will be interesting. So if I sound totally strange, say something in case the microphone's being weird. Anyhow, as Simone mentioned, we're here to talk about Tensor Processing Units, or TPUs, and how they kind of work, a little bit about their history, and how you can use them today. How you can program them, how you can get your hands on them, figuratively. And yeah, should be fun. We only have 40 minutes. The slides, I updated them, which really means I added more slides, so it was already kind of a tight talk, so we'll go right into it. To start with, I kind of want to talk about a little about why TPUs existed. There's kind of this story, tale of who here knows Jeff Dean? Jeff Dean? Ring a bell? We have one or two hands. He is the head of Google AI at Google, and he a few years back, like 2012, 2013, it said that he did some back of the envelope, napkin calculations, and realized that if all the Android users in the world used the text, speech to text, where you talk to your phone and it types for you, if they use that online service for 1 minute each day, they would consume more than all of the compute resources that Google's data centers around the world had available to them at that time. And so he realized that we needed more specialized hardware. And part of the reason that this was kind of happening was because the evolution of computer processors and chips is kind of coming to a bit of an asymptote. It's not going as fast as it used to, a few decades ago. And as a result, our computing demands as mobile and IoT and all of these use cases grow, and the number of devices grow, and the connectivity grows, all of this causes an exponential increase in demand, but our compute abilities are sublinear. They're kind of flattening out. So what we need is domain-specific hardware. We need something that is specifically designed for the use case rather than having it be general CPUs, right? And we already saw this happening thanks to the gaming industry with GPUs, but we're going to begin seeing this more and more in other industries as well. Bitcoin mining is another example of this, with all the ASIC chips that people have used to, mine the Bitcoin because the competition got too fierce. Another example is BigQuery. BigQuery is Google's big data warehousing solution. It lets you use like a SQL interface, but the underlying storage mechanism is not SQL. And part of what allows BigQuery to be so fast, and as a point of example, when I first used BigQuery, I did like what I thought was a big query. It was a terabyte of data. It read through a terabyte of data, and it did it in about 60 seconds. And I literally did not believe it. I was like, this is fake. The UI must be messed up. Because how can you read a terabyte of data, much less search through it and do manipulations on it in 60 seconds, right? Like it doesn't make any sense. The answer kind of lies in specialized hardware, specialized networking, and having basically everything in some form of memory rather than disk. So looking back at the TPU now, why did we need to make kind of domain-specific hardware for machine learning? And kind of back in the early days, they talked for a while. Welcome to big companies, I guess, right? And then when they really decided to do it, they really did it fast. For those of you who might be familiar with kind of chip design cycles, for example, Intel makes chips on this kind of tick-tock cycle, right? So that even though they're releasing chips every year, they have two separate teams that go work on 2-year cycles. And so they offset them like that, and they leapfrog each other. And so 15 months of chip design and production was a really, really accelerated timeline to create the first generation TPU. So this is TPU V1. And at this point, it is still in use, but is not something that Google is releasing publicly just because it's kind of an early stage product. It works, but it only does predictions. It only does inference. And the team quickly iterated on this and made TPU v2. And this is going to be kind of the practical portion of most of this talk, is the focus will be on TPU v2. And you can see from this picture the much bigger change, a big change in the size of the board, the number of processors on there. That's 4 processors on the board instead of just 1. The original TPU v1 fit into a PCI Express slot. So it was in the original, existing hardware infrastructure of the data center of those machines. Whereas with TPU v2, it's a separate board. And this picture is taken from above, so it's hard to tell. But what you're seeing here is each of these processors, the heatsink is actually quite tall. So if you viewed it from the side, you would notice that these are very tall stacks of heatsinks. And so these boards are loaded into trays in the data centers, and they have dedicated infrastructure and hardware for holding them. And we'll see some pictures of that shortly. Then earlier this year at Google I/O, we announced TPU v3, which they decided to use water cooling. Maybe it makes it shorter now, right, instead of air cooling. But again, there's 4 cores, and the extra density and smaller improvements in the microarchitecture has brought more improvements on the speed. Okay, so that's like the high level kind of. I fast forwarded to present day. Now let's go back and look at the beginnings of v1. The reason for that is understanding how TPU v1 works and why certain design decisions were made the way they were will help inform both how v2 and v3 work, as well as how you can take advantage of certain features, because having a kind of intuition about that underlying architecture will allow you to make tweaks to your machine learning models, to the way you do training, to the way you load data, etc. Okay, so in the first TPU, a relatively slow chip, right? Only 700 megahertz. We're used to seeing our laptops with several gigahertz of processing power. But the chip works in a very different way. It's operating in what's called a systolic array, and I think I have an animation of that later, so we'll look at that shortly. And we used it for things like you would expect: search, Google Photos, Google Translate, these kind of large machine learning tasks, especially for services that had a lot of users and demanded a fast kind of response time, right? You do a search, you want a response. You translate something, you want a response, like right away. And in terms of generalized comparisons between the first version of TPUs and the kind of enterprise GPUs and CPUs at the time, they were seeing very good speed ups in terms of performance, and importantly, performance per watt. Because in some sense, today's kind of technology is basically taking power, energy, converting them into compute, sending it over a network, and putting it in your phone, right? So the ability to turn power per watt into compute is a very relevant point. And so this, kind of broad point around the reasons for making TPUs and then kind of why it worked center around these 3 kind of points: reducing the precision of the chip, using kind of this systolic array or matrix processing, and then their kind of minimal design. So we'll talk through each of these 3 points in turn. Okay, so reducing the precision. In a neural network, I think as most of you know, it all kind of boils down to a bunch of matrix multiplies. You have your weights and biases, and you add them up. And so then you wrap them in an activation function, and then you have a bunch of those. And I think that's the end of, I have another one after this one. Okay. So then, that's like the forward pass. That's your, when you make a prediction, right? And so normally, when we're operating in, CPU land, or oftentimes even in GPU land, we're operating with 32-bit floating point precision, right? So that's 2 to the 32nd bits of precision. And so that means you can go both positive and negative quite far. And you can see this is a big number, right? This is 2 to the 38th on positive side and on negative side. And so a common practice to shrink things down, even especially for things like running on mobile or IoT or smaller architectures, is to quantize. And quantizing means that we're going to convert kind of values along this range into a set of kind of positions in the same range, but with less precision, right? So they're skipped It's basically exactly what you're seeing on the image. What's worth noting is that the distribution of these points may not be even. Oftentimes it's done during the training step, and you'll actually choose these bins based on the grouping of the values. So you might have certain clusters where the values are more closely spaced and further apart. And so with TPU v1, they used 8-bit precision instead of 32-bit precision. And thanks to that, you can get a lot more to fit on the chip, right? Smaller space. And there's a couple of things that are working to its advantage. Not only is it running a small, 4 times lower precision, it also, the chip itself ended up only needing to be quite a bit smaller, which improved kind of silicon yield. So that also drove down the price and cost of manufacturing these. Okay, so matrix processing, when we think about CPUs and GPUs, CPUs run in a very kind of linear fashion. You're doing a lot of back and forth right here, where you're computing something, one thing, and then storing the intermediate result, then doing something, fetching it, exchanging it back and forth. And then eventually you have an output. And then with GPUs, you can kind of do this in a more direct throughput way, and there's lots more smaller cores, and GPUs have gotten incredibly complex, especially in the past few years. And so what happens with CPU and GPU is that memory access becomes this issue, right? This going back and forth is very costly. And so the real best way that the designers felt that we can improve this is by kind of doing it all at once. And systolic arrays are not something that is kind of new. They showed up early in kind of compute, decades ago. But the idea is that you push all the values through in one shot. And the term systolic array, for those of you who might have a little bit of familiarity in biology or medicine, with the blood pressure, there's systole and diastole, right? Those two numbers, like 110/70. So systole, the systolic array, is referring to the fact that the numbers come through the matrix in this wave, in these waves, which is a little bit similar to how blood flows through your heart, right? The lub-dub, lub-dub. So this flow through the array like that. And so then, when you have a whole matrix of them, this is kind of, it falls through like that. And that enables you to have all, basically each pass can be one entire chunk. And perhaps a better way to think about this is to use the analogy of having CPUs be operating like a letter block printer. One letter at a time, boom, 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 boom. And then GPUs, maybe you're printing an entire line at a time, one full row at a time. And then TPU is printing an entire page at a time, right? So it's just kadunk, one page out. It moves over, and then another page comes down, right? So even though, for example, I mentioned that the processor runs at 700 megahertz, but now that you have the context of the fact that it's doing the entire page at a time, perhaps 700 megahertz doesn't sound so slow anymore. And so this is kind of the high-level diagram of kind of what's going on. The notable point here is this little bit here, the matrix multiplications. And so it's 64K or 65,536 matrix multiplies per cycle. And there's 700 million cycles per second, right? So the numbers start getting really big. And what's interesting is that instead of that animation where I had 3 values, 3 by 3 go through, this is much, much bigger. And because of that, you end up with a much larger amount of data getting pushed through the TPU on a per second basis. Okay, so let's see. We're going to skip ahead from that one. We'll come back to it in TPU v2. Performance per watt, much improved. This is normalized against CPU performance. And let's see, yes. And then finally, the design was all around kind of cutting down as much of the unnecessary stuff as possible, right? You'll notice the control logic only takes up 2% of the TPU. Much of the space is used for the matrix multiply, and then the activation function that comes after the matrix multiply. It's basically half the chip. Everything else is just getting the data in, pushing it out, various miscellaneous operations. Oh, and because of that, there's a guaranteed latency of 7 milliseconds, which is which I think it's pretty good. And then this is a brief comparison of in the V1 against this is a few commonly used model types, model architectures at Google internally. That's why they're coded this way. This is multi-level perceptron 1 and 2, like these two examples. And that's just your normal feed-forward deep learning network. And then there's two kind of language models, LSTMs, and then there's two image models, CNNs. And you can see kind of where V1 had more advantages or less advantages, depending on the type of model. Okay, so enough about V1. What can we use today? V2. V2, as I mentioned, it's kind of tall. A lot of heat sink layers. Probably kind of heavy, I would imagine. I've never held one. But let's see. Yes, it puts out about 180 teraflops. And that's per board. So that's 4 chips. And then each chip has 2 cores. Okay. So this is the layout of one processor, one chip. And this one chip has 2 cores. Each one has that big matrix multiply unit that we talked about. And then each core has access to 8 gigs of high bandwidth memory. That's what this HBM is. And you can see it here, these chips on the side of each core. And so, yes, the tensor core and then 2 cores per processor. And then we talked about that. And then, yes. So now the update to the microarchitecture is that instead of using 8-bit float, which was fine for predictions, but V2 shows up with predictions and training, right? So it can do the full gamut of operations. How can we still have good performance without losing so much precision that the training falls apart, right? And so the Google Brain team kind of invented their own float. That's why it's called a B float. It's a brain float. And the way it works is you have your 32-bit floating point number, right? And so these significance, these are the exponent bits on the left. You need 8 bits of exponent to reach the range of 32 bits, right? And what happens with 16-bit, the reason why the precision is cut in half is because the exponents are reduced by half. And so they can't represent as big or as small of values as 32-bit integers, right? They're not as precise, but they're also just not as big. And so what the brain team wanted was they wanted the full range of values. And so they kept all 8 exponent bits. So you see this and this are the same. And just said the actual decimals, the decimals that come after, we'll just drop a bunch of them. And hopefully that'll work. And so they tried it, and it kind of did. So it supports the same range as 32-bit, but only needs the space of 16 bits. And so that's like an interesting way to kind of solve that problem, right? Of I want precision, but I also want speed, and I don't want it to take up so much space, because manufacturing these chips with 32-bit precision becomes very costly because the silicon yields problem. The chips become too big for the silicon wafers. All right, so cloud TPUs, running TPUs in the cloud and giving you access to them. What does that look like? I thought I changed that slide. Is there? Okay, ignore that slide. This slide is the one you want to pay attention to. So this is the updated pricing, and as you can see, they got lower. But basically, in Europe, access to TPU v2 is about $5 to play around with. And obviously, when you first start using Google Cloud, there's a bunch of credits they give you and stuff. So it's a low enough price point that I think I can pretty reasonably say you can experiment with it. You can test it out and basically not have it be a burden. Oh yes, and you're probably wondering about the preemptible TPUs, because that is a much, much lower price. So preemptible TPUs are billed by the second, I think. You're not billed if it shuts you down within the first minute after you start it up, things like that, but also a great way to experiment with it. And for those of you who are not familiar, preemptible means that I give you this resource, but I can take it away with some amount of prior notice. And so, let's say, whereas the other one is guaranteed, it's saying, I'm going to pay $4.95 and I will always have access to it for as long as I feel like it. Whereas preemptible, maybe someone else wants it and it goes away. But then you can just go get another one. So as long as you have the code to just manage that and have the checkpointing to take care of not losing data in between, it doesn't end up being that big of an issue. Okay, and then V3 with the water cooling, it's still in beta, and that has a little bit more expensive, but a little bit more performance. So it's kind of your trade-off. And then again, same thing with the preemptables. So all of this obviously is available online. I just want to kind of point it out. From a while ago, Stanford created Dawn Bench to benchmark different kinds of models being trained on different kinds of hardware, right? So it's not just performance of models, but it's models on specific hardware. And so a couple of examples of kind of training models to a state-of-the-art level performance, how long it takes, how much it costs, things like that. So this was a couple examples. This is ResNet on V2, and there was kind of an optimization that came later that FastAI came up with, a couple of tweaks to the way the images were loaded and cropping, and that dropped it down another, 50% or more. So that was neat. Let's see. Yes, okay, so that's the first part. What is TPU? Now, on to the second point, the TPU pod, right? So we just talked about the board, the chip, the architecture. Now I want to talk about using them in a distributed system, right? Using them in a large scale. And so today, there's a number of different high-performance computing technologies available, right? This is one example of it, of NVIDIA's kind of large, I think it's, what is it, the DC GAN or something, or DGX, sorry. And so that's about, what is it, $400,000 to get you 2 petaflops of power. It's 16 NVIDIA V100s. And it's one, big supercomputing box. I mean, I guess it's bigger than a box, more like a room. And so you can get these kind of TPU clusters. These are V2 pods, and there's 64 of those boards in one of these. And just to give you a little lay of the land, what you're seeing here is over here is 32 TPUs. Over here is another 32 TPUs. You can kind of tell, right? There's 1, 2, 3, 4, and then there's 1, 2, 3, 4, 5, 6, 7, 8 going down. Now the question then becomes, what are these? And what are those? So all the TPUs are connected to virtual machines, like normal computers. So the TPU board, that's really all that's here. It's just the TPU board. It's not connected to a CPU. It's not connected to main memory. There's no disk. There's a lot of stuff that's missing, right? It's just the TPU. And all of that lives over here. So each TPU is connected to its own dedicated host. It has a host machine that it lives on. And unlike V1, TPU V2 is not going to just slot into the PCI Express slot. Right, so it has custom high bandwidth interconnects, and that's what you're seeing with these cabling here. All right, so remember, 64 TPUs per pod. And what they're doing is they're connected in what's called a toroidal mesh. It's hard to say, but it basically means that you can use a pod or a subsection of a pod, however much you want to allocate, as one machine, effectively. All the low-level stuff, Google, take care of it. Your code for one TPU is essentially the same as 64 TPUs. And so you're basically getting a supercomputer for TensorFlow. And when you look at scaling, this is, it's not the best graph in the world. I'll improve it someday. But basically, there's 64 TPUs, right? And so this graph goes out to, around 64. That's the point. And so this is the scaling up to 64 TPUs. And we're seeing that it's linear. And compare that in terms of, when you have a high-performance computing cluster, it's just one big box. It's a big box, but it's once you utilize it all, right, that's as far as it's going to go. It just stops there. You can't just get another one. What are you going to connect it with? Gigabit Ethernet or something? It's not going to work. So that's kind of an interesting effect there. Okay, pod pricing. So this is an alpha, and you can get up to a full pod at $400 an hour. So it is per hour, and then that goes down to as little as a half, quarter, an eighth of a pod or so for far less. Okay, so now you're looking at this and you're saying, what is a pod slice? So a pod slice, right? Pod slice is a subsection of this pod. So here's the example. Like I mentioned, this is 256. Sorry, this is 64 TPUs. This is a half pod, right? In blue on the right, and then the green box is a quarter pod, and I guess the yellow box is a 16th of a pod. But now you're seeing these numbers, right? We saw those numbers earlier too. Like these, this doesn't look like 64 TPUs. This, what is it, 512? What does that mean? And so the reason is because one TPU pod has 64 TPUs. Each TPU has 4 processors, and each processor has 2 cores. And for reasons that are above my pay grade, they've decided to represent the TPUs in terms of cores rather than in terms of TPU boards. Okay, so understand that half pod is 256 cores and 512 is your full pod. On a TPU V2 pod, this is a half pod, so it's only one side of this image, where you're training something like ResNet to full performance in 30 minutes. For those who were kind of pay attention earlier, earlier for one TPU, I think it was half TPU V2, ResNet 50. Here we are. Training time 8.5 hours. Right, same network. Now we just got 32 of those boards hooked up together, and we end up at, instead of 8.9 hours, 30 minutes. So pretty amazing that we can train a state-of-the-art image model on, the full data set running through at 77,000 images per second, right? Pushing that data through those arrays. Those big arrays can just eat up those images. And you can reach state-of-the-art accuracy in 30 minutes. And so some other kind of examples. RankBrain is one of the models that does ranking for Google Search. So training the entire Google Search model, as you were. 9 hours on a quarter pod. The image model for things like photos and such, or an image model example, moving from the old whatever they were using before, CPUs or such, on again a quarter pod, less than a day, and generating speech. So for example, when you do voice synthesis and stuff, generating at 20x real time. So enough to keep up at least, right? And because the TPUs are so big, and remember there's 8 gigs of memory per core. And there's 2 cores per chip and 4 chips per board. So that's some ridiculously large number of gigs of memory per board, right? And so it allows you to load way bigger batches of images. Okay, so when you're training something like ImageNet, from ImageNet, they're loading in a batch size of 8,000. So like, for those of you who have trained ImageNet before or done image models before, you can kind of think about like, what does that mean? Like being able to train at that kind of batch size allows you to hit state-of-the-art accuracies much faster, right? It just shoots straight up, basically, instead of kind of taking its time, which is pretty crazy. Okay, TPU v3, not a whole lot to say here, other than that you can test it out and stuff. In terms of the hardware, it looks like that. They put more of them, and you hit 100 petaflops. It's a nice number, but it's liquid cooling, the densities are higher, and overall, as a pod, you're getting 8x performance. All right, so that's the pod story. Now on to programming it, right? How do we code for the TPU? And so, firstly, I want to call out that this isn't always true, but the docs in this case are actually quite good, and there's a lot of good examples to use. There's a lot of reference models and things that you can just kind of take off the shelf, run it, see that it works, and then tweak them for your use case, or replace the data set, or change the optimizer. Like you can just start playing with it rather than starting with a blank editor. Okay, so using estimators, specifically what's called eventually, right now it's TPU estimators, but eventually the idea is that estimator will allow you to handle all of these use cases, whether you're training on CPUs, bunch of CPUs, GPUs, a bunch of GPUs, TPUs, a bunch of TPUs, to be able to handle all of that with the same API, the same code base, right? With like configuration tweaks and flags to indicate like, if it's distributed, use this configuration. But for the most part, the idea is to keep the code as kind of maintainable as possible. And so with that said, the current state of events is that there is a specialized estimator for TPUs. And so there's this TPU estimator, and there's a couple of more flags to give. For example, there's a use TPU flag, right? Like, do we use TPU or not? And this means you can use the same code, right, by just flipping a flag and run it locally on your laptop and have it run on CPU. And test it out, make sure things are working, make sure your TF data pipelines are correct. You don't need to be using the TPUs and getting a syntax error, or using the TPU and getting some kind of data loading problem, right? So the preference is to use kind of a hybrid approach when it comes to testing and then deploying. Okay, so a small example, this is a custom model, and the part I want to focus on is down here. We have your choice of optimizer, and then you return your estimator spec. So this is like your normal run-of-the-mill, in this case it's a CNN, and to make this kind of work for TPUs, what we're going to see is we're going to add a wrapper around the TensorFlow optimizer called a cross-shard optimizer. The name doesn't really matter, you just add the line in. You can basically copy paste. And then instead of using the standard estimator spec, you're going to use the TPU estimator spec. Okay, so what is happening when you run that code, right? Like, there's a lot of stuff that is being done on your behalf that is worth kind of just having an awareness of. And the way it works is we've been talking a lot about the bottom layer, the cloud TPU itself. Now, the TPU, as I mentioned, is tied to that host. There's that machine, the machine right next to it that it's directly physically connected to, and that's the cloud TPU server. It has a outward-facing kind of service that has an API, and then it has a cross XLA, accelerated linear algebra compiler to compile it down to kind of TPU bytecode, basically, right? And then you get your own VM that you connect to this kind of pair for you. So that VM lives somewhere else in the data center and is connected through via Ethernet. And so that's kind of where your code runs. And part of it is for security, part of it is for just performance, like the way this is architected. And so what's happening here is there's two virtual machines you have to think about, right? There's your virtual machine on Compute Engine, and then there's the host CPU, that machine that is literally physically connected to the TPU itself, and that's why there's that box around it. And so that high bandwidth memory is operating as a queue for the data. So each core has each chip has two cores, and so you have two of these per thing. So it's got to keep it straight, but basically all of that is handled on the board itself. So you load a lot of the code into the TPU eventually. And so then the data is going straight into the host CPU rather than kind of going through here and then coming around. It will connect directly to it. And so here, your CPU, your compute engine instance will basically just be sending instructions of saying like, here's what I want you to do. This is where the data lives. Here's the model. Here's the parameters and configuration. Go. And then as it does the training, for example, the metrics come back and you can write your checkpoint files to a location of your choice. Okay, so stepping back a minute, let's talk a little bit about intuition around what TPU is good for and maybe not so good for. Because of the large matrix array setup of the TPU, it's going to be really good for, today, it ends up being really good for a lot of image-related tasks. But there's also kind of ways that you can take your non-image data and turn it into formats, structures that are more amenable, are more suitable for pushing through the TPU, right? If you can put it into a big matrix, then it starts making more sense. The other thing worth pointing out is that that matrix size, the actual size of the matrix in the chip itself is relevant. For example, if you had an image that was 1 pixel too big, bigger than that matrix, what's it going to have to do? It's going to have to kind of cut that up a little bit and then do another pass just for that extra 1 pixel border, just to get it all in, right? So you don't want that. Best case scenario, you have it fit perfectly each time so that the batch sizes are exactly what the hardware expects. And so we're kind of entering this era where, if we remember back to the beginning of this talk where I talked about domain-specific hardware, that kind of implies you're going to need hardware-specific code to some extent, right? We're not doing assembly programming here, but at the same time, having an awareness of what you're getting into is important. Okay, so yeah, small, also the precision aspect of it, right? Because it's a 16, technically actually still a 16-bit-ish, right? The brain float 16-bit value. There are certain things that may not be as suitable for it if you really need that high precision performance. And then finally, of course, the TPU currently, at least in V2, V3 state, only supports a subset of all the TensorFlow operations. And so you'll still have to do certain things on the host CPU. Sorry, the host CPU. So that's, again, this CPU, not that CPU. An example of that would be JPEG Decode. That operation happens here. And then once it's turned into just numbers, then it goes to the TPU. So another way to think about it is that if you have, this is like a Ferrari. It's a race car. You press on the gas and it's going to go. Oh, wow, I just said Ferrari. We're in Italy. That's funny. Okay. That was unintentional. And then, if you have something where you need careful driving and maybe you're doing a lot of dynamic updating as you're going along, maybe the TPU isn't the best use case. There's already a bunch of reference models for different kinds of use cases, and there's constantly more coming. I think this slide is already no longer current. There's already more, so there's just constantly more coming. And yeah, so in summary, the TPU is this great chip. It has kind of an interesting history, if I say so myself. We've got pods, so you can do a lot of compute on a TPU, and finally, it's available today, and I'd encourage you to check it out. G.co/cloud TPU, or I'm sure if you search for TPUs on your search engine of choice, you'll find it. Yeah, my name's Yufeng, and thanks a lot. I also have, if anybody is interested, I also remembered, I do have some TensorFlow stickers. They're a little bit small. I know there are giant ones somewhere that people have, but it's just the logo. It's a little more compact. It looks something, it looks something like that. So it's cropped. It's not a hexagon for those of you who really like hexagonal stickers, but yeah, it's a neat little thing. So if you guys want some, I can't throw them at you, so you'll have to walk up here yourself.
Okay, thank you, Yufeng. If anybody has a question.
I think they're saying I need headphones.
It's okay.
Oh, they can't hear you.
Thank you. If anybody has a question, please raise your hands. Okay. I'll give it to you. Just to listen.
Hello.
Hi.
I got two questions for you. The first one is, are you going to support the Keras API? And the second is, do you have or do you plan to have any debugging or monitoring tool to understand the usage of TPU units in a pod?
Yeah, so the first question, I don't remember. I'm sorry. At one point, I thought I heard something about Keras or not. I honestly don't remember. Right now, there's no official result on that. But hopefully, I'm I'm hoping that is the case as well. I'll support Keras on TPUs, but yeah. And then the other point around, sorry, I forgot. I'm trying to remember.
Yeah, the second point was once you deploy your monitoring. Yes.
So yeah, I had a bunch of slides on kind of performance and monitoring tools, and they do exist. It just didn't have time to show them today. But yeah, there's a whole set of them, and there's yeah, both in terms of on your local machine for command line interface work, as well as kind of web-based things to look at utilization, to look at performance and throughput and such. So yes.
Okay, thanks. Any other question?
What about TPUs on the edge? I see you didn't mention that, that they were quite interesting when they were released.
Yeah, so there's kind of this newish project to kind of put TPUs in edge-based devices. They're pretty new. I think you can you get them yet? I don't remember.
I don't think in Italy.
Yeah. But yeah, basically they're super new. The idea basically is it's running high performance for edge, right? Not literally a TPU, but it's a different chip, but it's taking a lot of the same principles. I think it only runs inference, so you're expecting kind of 8-bit performance, and you would tie that to say your Arduino or Raspberry Pi. Yeah.
Thanks.